Okay, so 5.2 talks about multiplication and division of integers. Okay, so we're going to discuss for multiplication first models, and two models will be a chip or charged field model like we had for addition and subtraction, and number line model. Let's start with the chip model. So if you have multiplication by a positive number 3 times negative 2, then that means that, so if one of the numbers is positive, that means you can think of it as three groups of two red chips, right? Red chips stands for negative, or three groups of two negatives. So basically you can, if you don't feel like drawing chips, you just draw three groups of two minuses, right? So that's one group, second group, and third group. And so combined you can see that you have 6 minuses, so you can say that this is equal to -6. Okay, but what if both numbers are negative? By the way, something to point out, if I switch the order, since multiplication is commutative, you can say that it's the same as 3 times -2 and proceed same way as we just did, right? But what if both numbers are negative? How to interpret that? Well, from that you can say, when both this is negative, you can say we're going to have to remove three groups of two red chips, or we will have to remove three groups of two negatives. But remove from where? From what? Well, the starting point would be 0. So if you have 0, remember, I'm going to have to remove three groups of two minuses. So I'm thinking, okay, I create three groups of two red chips. But of course, I started with nothing. So I have to, every red chip will have to be balanced by a positive yellow chip. So that this is like my 0, right? Because red and positive chip cancel out. And now I can remove three groups of two red chips, and that will leave me with 6 positive chips. So +6. Again, if you didn't feel like drawing chips and coloring it, then you can just represent that with minuses, right? So I start with 0. Since I'm aware I'm going to have to remove three groups of minuses, excuse me, then I have to first create as many pluses as minuses. So that puts me at 0 at the beginning because I didn't start with anything. And now I can remove those three groups of two minuses. And if you remove, you're going to end up with 6 pluses, right? So the same thing, except for chips, I'm using pluses and minuses. Okay, so let's see if we can imitate that. Let's start with the first example. So demonstrate each of the following multiplications using the charged field or chip model. Okay, so let's see what to do. So now here we can use the fact that either we could use the fact that the multiplication is commutative, so 3 times is the same as 3 times -5, or we can we can use the fact that this is the same as 3 times -5, or we can think of this as we're going to have to remove 5 groups of 3 pluses, right? Because remove because of the minus 5 groups of 3 pluses. So remove from nothing. So with the beginning we start with 0. So since I'm going to remove 5 groups of 3 pluses, then let's draw 5 groups of 3 pluses. So 3 pluses, that's 1. That's second group. That's third group, fourth group, and fifth group. Then I have to balance them out with the same number of minuses. So each group of pluses will have group of minuses. So 5 group of minuses. So that's like my starting point. And then I can remove and those 5 groups of 3 pluses, right? And when I remove, what that will be equal to is, well, 5 groups of 3 minuses, right? I wish I had a little bit more room here. Maybe let me, this group I'm gonna write here. So you're going to be left with basically the minuses. So 5 groups of 3 minuses, which is 15 minuses. So that's equal to negative 15, right? So another approach would be to represent this, use the fact that multiplication is commutative and write it as 3 times negative 5. Then that would be just writing 3 groups of 5 minuses, right? So 1, 2, 3, 4, 5, that's one group. 1, 2, 3, 4, 5, that's second group. 1, 2, 3, 4, 5, that's third group. So this is 3 groups of 5 minuses, which of course we realize it's negative 15. Okay, that's one example. Let's look at another. So negative 6 times negative 2, right? Well, here there is no way around it, because multiplication is commutative, but both numbers are negative. So we have to go with this approach of removing. So that would stand for remove 6 groups of 2 minuses. Because minus 2, we think of it as 2 minuses, right? And 6 remove because of this minus, and 6 groups, right? So remove, but remember you're starting with nothing. I'm going to make a big circle. So 6 groups of 2 minuses. So I'm going to draw one group of 2 minuses, second group, third group, fourth group, fifth, and sixth. Since I'm supposed to start with nothing, then every group of minuses will be counteracted by the same group of pluses. So now you can remove those, and what you're left with is, well, your pluses, right? And you're left with 12 pluses, right? So that's positive 12. Okay, so that's a chip or a charged field model. Let's look at number line model. Number line model works the same as before, meaning we always start at 0, facing east or right, positive direction. Now, if the number is positive, we walk forward. If the number is negative, we walk backward. Now, if multiplication would here mean 2 times 3, it means we're gonna move twice 3 to the right, right? Twice positive 3 means we're moving to the right. So this is representation of 2 times 3, the first number line. We're moving twice 3 units to the right. Now, what about 2 times negative 3? So if one of the numbers is negative, then put that negative number at the end, and think of, and since the other number is positive, think of it moving twice 3 backwards, because -3 means you're going backwards. So look at this cat here. The cat went 3 units backwards twice. So it ended up with, oh, I didn't put the solution. We of course read where the cat ended up being. Here at 6, here at -6. So marked in those circles here in blue is where the solution is, what the solution is, where the cat ended up being after making the move, right? Okay, but then, so that's when one number is positive. But what if both numbers are negative? So you cannot place any positive number up front. Both numbers are negative. So how to interpret that? Well, for that, you do 2 times -3 first, because you're thinking of this as being the opposite to 2 times -3. Okay, so basically what I'm trying to say is that you do 2 times -3, which means you or the cat moves twice 3 backwards, right? So it ends up at -6. And now this minus stands to the opposite of that, right? Because we just did 2 times -3 meant going twice 3 backwards, so ending up at -6. But then I have to do this marked in pink, and this negation, or this finding the opposite of that. So then we kind of, the opposite to -6 is 6, right? So the cat would then be kind of transferred across the 0 to the other side of the axis, right? Number line. So the answer to that is +6. Okay, let's try to do some number line models. So let's try to do the first one. So -5 times 3. Okay, if one of the numbers is positive, then the thing here is to place it first, because multiplication is commutative, so you can change the order. So I think as going 3, right, times, or 3 groups or times 5 units backwards, right? So basically I start at 0, or right, I'm gonna draw a person instead of a cat. We're always facing east, right? That's why I drew hands this direction. And then I'm gonna go 5 units, 3, 4, 5 units backwards 3 times, right? Maybe I need to shift it. So I'm gonna go 3 times 5 backwards. So what, that will be my one -5, then I need another -5. So -6, -7, -8, -9, another 5. That brings me to -10, and another 5. That will bring me to, right, so I'm moving backwards 3 times 5 units backwards, right? So I end up at the end here, still facing east, right? But I ended up, if I went backwards 3 times 5 units backwards, I ended up at -15. So the solution reading from the number line is -15. Okay. Okay, so let's try to do the next one. So I think of it as -6 times -2. So as before, I'm gonna go 6 times 2 units backwards, right? But at the end, I'm gonna translate it, so that's 0. Okay, that's, so I will go, this inside means 6 times 2 units back, okay, backwards, which means I start at 0, right? My hands show me the direction I face. I always start facing east. Then I'm gonna go 2 units backwards 1 time, 2nd time, 3rd time, 4th time, 5th time, and 6th time, right? So 6, every time I go -2 and I do that 6 times. So that's gonna bring me to -12, but that's not a solution, that's just this inside. But now I need to reflect it across 0 because I'm looking for its opposite. Okay, so that will bring me to +12. Okay, so that's the number line model. But of course, if we were to observe and we know it, if we were to think of the how this number line or chip model, what it produces, it shows that, okay, if both numbers are positive, then we're just multiplying whole numbers, which we know how to deal with. If both numbers are negative, then the product will end up being the same as the product of their absolute values. So basically, we will ignore the negative signs. For example, -5 times -2 will end up being, well, absolute value of -5 and absolute value of -2. So basically 5 times 2, which is 10. And we know that when we multiply two negative numbers, we end up with this +10. Minus minus gives me plus, but that's formally that's what you would write, that you really are multiplying their absolute values, right? And if one of the numbers is negative, the other is positive, then here's like multiplying their absolute values like before, except that I know the entire solution will be negative. So negative number times positive will give me, I can rely on multiplying whole numbers because I just multiply their absolute values, but I know it will produce a -10, right? So negative at the end. Okay, and we know those rules, just something that we would have to lay out to kids we're teaching how it works. Not maybe necessarily with absolute values, but with the concept that you just, when you multiply, you can say, okay, I ignore the signs, I just do 5 times 2, but then I know that, at the end, the solution will be negative because one of the numbers is negative and the other is positive. Okay, guys, we have the following property of multiplication of whole numbers, the same as we had for integer numbers, the same as we had for whole numbers. We had a closure property. So if each number is integer, their product is an integer number as well, which makes sense. We're not going to have get a fractional number when you multiply two integers. Multiplication is commutative. That means a times b and b times a is the same. You have associative property. So if you multiply 3 numbers, you can group any neighbors, right? So you can first multiply a with b or then b with c. Then you have so-called identity property. So one is the identity for multiplication, because when you multiply any number by 1 on either side, doesn't matter, it's not going to change it. It's still a. So that's called, one is called identity for multiplication. You also have distributive property of multiplication over addition. A times b plus c is ab times ac. And notice if you do, ab means a times b, ac means a times c. If you don't see operation explicitly written, then it just means multiplication. And on either side, if A is on the right side, that also means that this A will be distributed. So B times A plus C times A. Now, I'm not going to overcomplicate it, because if you that with the combination of the fact that the addition can be written as subtraction can be written as adding the opposite, you can actually notice that if you were to multiply it by A, then using the fact that multiplication is distributed among the sum and few other properties allowing you to pull this minus in front and change that back into the difference, basically you can realize that also multiplication is distributive over subtraction, because subtraction can be viewed as adding the opposite, right? Okay, so that's what I want to point out here. I don't want to get into much details, but we have distributive law of multiplication over subtraction. Here was supposed to be minus, not plus. Same as over addition. And finally, you have zero multiplication property, that anything multiplied by 0 is 0. Right, so that's the main thing. Okay, so let's use this distributive properties of multiplication over addition to simplify those expressions. Let's start with A. Negative 3 times x minus 2. So it says that multiplication can be distributed over subtraction. So we do negative 3 times x minus negative 3 times 2. So I distributed this multiplication over subtraction. So it multiplied x and it multiplied 2 and subtraction remained, right? But that's negative 3x and then minus. Now negative 3 times 2, right? Because first I need to multiply. That's, we know, is negative 6. Positive times negative gives me negative. And then I know that since subtraction is the same as adding opposite, I can think of it as plus negative 6. And that's actually negative, opposite to opposite is 6, right? So that's going to be negative 3x, right? And what happened? Remember, this subtraction can always be written as adding the opposite. That's what I did, plus minus. Just to be very strict with all following exact rules we had laid out, but all of us know that minus, subtracting negative is like adding a number, but this is the exact explanation why. Okay, well, let's do B. A plus B times A minus B. This one is tricky because technically I don't have a foiling rule, but I can think of, for now, I can think of this as one whole thing, one number. I'm not going to break it. I'm just going to distribute it over this difference. So notice, if I think of this as a whole thing, one number, then I use distributive property of multiplication over subtraction to write this in this way, right? Okay. Then I'm going to use distributive property of multiplication over addition to distribute this multiplication by A. So A times A plus B times A minus, and here I will have A times B plus B times B, okay, which is really A times A is A squared. B times A is the same as A times B. What property I'm using? Commutative property. Now I'm going to use that minus can be distributed among the addition too, because why is it so? Well, because I can think of, there are a few ways to look at it. One way is that I can think of here first using the fact that minus is the same as plus minus, and then distributing minus among the, because we know that the opposite of sum is sums of opposite, but I don't want to complicate it. We know from algebra we can distribute minus, and b times b I can write as b squared. So notice a times b cancels out, the same thing, and we end up with a squared minus b squared. So we just kind of created what we did. We used the property of distributive property of multiplication over addition, but in fact we also know that that will boil down to whenever you have binomial times binomial, the easier way would be just FOIL it. We can develop that rule that you multiply a by a times b, b times a, which is the same as ab, and b times b, negative b. And we have this shortcut of foiling instead of using this distributive property of multiplication over addition like we did if I wanted to strictly follow the rules. Okay, so that's the way you would probably do it, because we know how the foiling works, right? Either way you're gonna do it, as long as it's correct, is fine. That brings us to the formula that whenever you have, I'm gonna use capital A and capital B. Whenever you have a difference and a sum, with either way you start is the same. One is the difference, one is the sum. Doesn't matter which one goes first. That will become the difference of squares. Okay, this is a difference of squares formula. So let's use that instead of foiling every time. Let's use the difference of squares formula. So for me to know that this is applicable here, I looked at this is the same for B. In both cases this is the same, and the only difference is that one time you have a difference between, the other time you have a sum between, right? So I know that becomes 4 squared minus b squared. You take the difference of squares of the terms, those two terms involved, 4 and b, right? So that's 16 minus b squared. Now let's look at this one. Okay, so what two numbers I see? Negative 4, that's 1. The other one, that's b, and they're separated by plus and the other time by minus. So I know this will become their difference of squares. So negative 4 will have to be squared and b will have to be squared and their difference. But negative 4 squared, negative 4 times negative 4 will be positive 16, right? We established the rule that if both numbers are negative, we're really just multiplying their absolute values. Okay. But we can go the other way around, and before I move to C, let me do something easier. What if I wanted to do the other way around? If I had the difference of squares, but I wanted to factor it, for example. Not that this is part of this problem. If you have a difference of squares, you can go the other way around. You know, imagine kind of erasing the squares and then writing the same but with the sum. You know that it goes both ways, right? Okay, so let's do this example. So since I see a difference of squares, right? This and this and this, they're squares. So now imagine remove the squares. That's going to be your one factor, and then write the same but with the sum in between. So think of this like being your a and this like being your b. So you have a squared minus b squared. It became a minus b and a plus b, right? So again, imagine removing the squares, which will create the one of the factor, the difference, a minus b, and then write the same, but instead of minus in between with the plus. That's how this, that's exactly what we did above. It was just easier, right? With difference of squares here, x squared minus 3 squared was less complicated. Now our a is x plus 3 and our b is x minus 3. But nevertheless, this will help us simplify it because now I can subtract it. So subtract this one, x plus 3 stays the same because there's no minus or number in front of this parenthesis. Here we will distribute minus minus 3 will give me positive 3. And here we will also drop parentheses. Here nothing to distribute, so it stays the same. Notice that here x cancels out, so it's just 6. No need to keep it enclosed with brackets, so just 6 times. And here, well, if you combine like terms, it's going to be 2x, right? Because here 3 cancels out. So actually it's going to be 12x simplified form. Okay, so that was a tricky one. Let's keep following this thing and let's keep factoring. So if I can write something as difference of squares, then remove the squares, it gives you x minus 3, and write the same with the sum. And this is you know, difference of squares playing out. Same here. You have difference of squares, remove the squares, that's your one factor, and then write the same instead of a difference, the sum. Of course, here I'm going to simplify because I will drop the parentheses here and minus z, nothing to write now. So now brackets are not needed. I can write parentheses. And the same here, I will drop those parentheses and plus z. And that's the factored form. Okay, what about here? Well, that's not a difference of squares, but what can I factor out? X. Because I know that using, it's kind of like reversing the distributive property, right? If I take out x, now I always can check back if you were to distribute multiplication by x, so 5y, not x. If you were to distribute multiplication by x, will it be the same as the original expression? Yes, right? You would end up with minus 3x and plus 5xy. What can you factor out here? Well, only 3. Now, notice that to really truly see how the factoring out works, you would have to write 6 as 3 times 2. So now you see that common factor that can be pulled to the front, and you end up with x minus 3. And you can check if you were to distribute multiplication over this difference by 3, then you should end up with 3x minus 6, right? What you had originally. And finally, there is here nothing really. I know some of you would say, well, this is 3x squared, but why can we actually add or subtract like terms? Well, because it relies on factoring x squared out, and then what you're left with is subtracting the numbers.